In Chapter 9, we will be discussing polymers and plastics. In the process, we will discuss why plastics are important, what happens when they are recycled, and the downside of recycling. What do you think about when you think about plastic? Do you think about bottles? How about recycling? Do you think about nylon or styrofoam? Plastics are more a part of our world than you may realize. Plastics are polymers. So what is a polymer? Polymers are large molecules made up of long chains of atoms covalently bonded together. They're made up of monomers. A monomer is a small molecule used to synthesize the polymeric chain. Think of it as a paper clip and then linking all the paper clips together to create the polymer. Polymers have been with us since the beginning of time. Natural polymers include such things as cellulose, starch, tar, and shellac, tortoise shells, and horns, as well as tree saps that produce amber and latex. These polymers were processed with heat and pressure into useful articles like hair ornaments and jewelry. Natural polymers began to be chemically modified during the 1800s to produce many materials. The most famous of these were vulcanized rubber, cotton, and celluloid. The first semi-synthetic polymer produced was bakelite in 1909 and was soon followed by the first synthetic fiber, rayon, which was developed in 1911. The polymers, poly, which means many, can be formed from the same type of monomer or from a combination of monomers. For instance, A is just one monomer. B is the same monomer linked together several times, whereas C is the two different monomers that are linked together, just alternating. Polymers are referred to as macromolecules because they involve thousands of atoms and their molecular masses can reach over 1 million. Many common classes of polymers are composed of hydrocarbons. We have seen hydrocarbons in the past when we discussed non-renewable energies. Carbon makes up the backbone of the molecule, and hydrogen atoms are bonded to the carbon atoms. This diagram is polyethylene, the simplest of the polymer structures. Other examples of polymers that contain only carbon and hydrogen include polypropylene, polybutylene, and polystyrene. You'll find pictures of these on page 378 in your textbook. They're used in things like bottle caps and CD cases. In addition to polymerization, the monomers simply add to the growing polymer chain in such a way that a product contains all the atoms as the starting material. Notice that originally there are 2 carbons and a double bond. Notice that there is a 2 in front of the monomer. They end up getting linked together to have 4 carbons in a row. As additional ethylene molecules join, the chain grows. These continue getting linked up. This is the only product and no atoms are eliminated. This then reduces the waste. Polyethylene is a soft, flexible plastic used for bags, bubble wrap, and toys. This picture is the formation of polymerization. The double bond is broken. These 4 dots represent a double bond. The double bond is broken, and those electrons are then linked to the next monomer. So notice that there's an extra electron here. So that extra electron gets linked up to the next one. And so instead of having 4 dots here, it now only has 2. Meaning it's a single bond now. The overall process is the linking of the carbons. Notice on the left-hand side, there is an N in front of the ethylene. Then notice that there is an N at the end of the product. This is indicating that however many ethylenes are added are the quantity of repeating monomers in the chain. Notice that there are no carbons or hydrogens that are lost in this process. It doesn't say plus something else. It just simply says the product. If one of the hydrogen atoms on ethylene were replaced by chlorine, the process of adding them together are the same. We simply have a chlorine where a hydrogen would be. The result of the formation is polyvinyl chloride, or PVC. It creates a rigid, shiny plastic. PVC is used for plumbing, pipes, house siding, or hotel room keys. So by changing that one element, greatly changes the chemical properties and physical properties. Let's take a closer look at polyethylene. That was the first one we talked about. It can be used for plastic wrap, plastic baggies, or milk jugs. It's the same monomer. How can it have so many different characteristics? Think of polyethylene as spaghetti. Imagine the molecules are as long lines of carbons that are gathered together on a plate. They may be touching or overlapping, but they are not connected to one another, just like a bowl of spaghetti noodles. The thing that is holding these chains of carbons together is called intermolecular forces. One that we have already discussed in previous chapters was hydrogen bonding, when we discussed the interaction of water molecules to solutes in solutions. So intermolecular is between the molecules. In this particular case, the intermolecular force that we are keeping polyethylene together is called the dispersion force. These are attractions between molecules that result from the distortion of electrons that cause an uneven distribution of the negative charge. They can be rather significant with very large molecules. So it's very similar to the hydrogen bonding because we have a partially positive and a partially negative. However, it's not as strong. The attractions are not as strong. The pictures in this slide is a demonstration of a dispersion force. As you pull the plastic bag in opposite directions, the bag gets thinner in the middle. The molecules in the middle start to line up a bit. This alignment is making it thinner in the middle. If we try to compare plastic wrap to a milk jug, we notice a lot of differences. They are made of the same monomer, ethylene, but they look and behave very differently. Plastic wrap can be stretched, while milk jugs are more rigid. So what accounts for these differences? One way to make the molecules behave differently is to change the way they are bonded to each other. For instance, you can have them in a long strand, like those on the left-hand side, Or you can have monomers branched off like chains, like you do on the right-hand side. On the left, you have high-density polyethylene. They are greater in density because they're able to stack upon each other. It also makes them stronger, more rigid. The plastic is better for milk jugs and items like toys. On the right is low-density polyethylene. These are used for plastic bags. The branches make it so the molecules do not interact as much, therefore reducing the dispersion force. There are over 60,000 synthetic polymers today. There is more plastic produced in the United States than steel, copper, and aluminum combined. The 6 polymers on the next two slides, make up 75% of all the plastics produced in the U.S. All 6 are considered thermoplastics, which means that they can be melted and reshaped over and over again. Some are considered to be crystalline solids, which means their long polymers are arranged neatly and tightly in a regular pattern. These tend to be harder structures. If you missed that definition, it is on page 377 in your textbook. Others are considered to be amorphous solids, where the molecules are found in a random, disordered arrangement, and their packing is much looser. That is on page 378 for amorphous solids. These tend to be more flexible. Here are 3 of the most common polymers known collectively as the Big 6. So here are 3 of the 6. We have already briefly discussed high and low density polyethylene. And we also previously mentioned polyvinyl chloride, or PVC, and how chlorine is in place of one of the hydrogens. Many different arrangements are possible when polymer forms from polyvinyl chloride monomers. How do these different arrangements affect the properties of polymers? For instance, here, considered head to tail, which means chlorine, hydrogen. This is head to head, tail to tail. The chlorines are right next to each other. And then this is a random arrangement where sometimes they're spaced out, sometimes they're close together. If a manufacturer wishes to make PVC more pliable, like in a shower curtain, they may choose to add small amounts of plasticizers. The polystyrene foam used in styrofoam cups is made in the same addition process. The addition to this reaction, a blowing agent, is added to the formation of styrofoam. It's a gas with a rather low boiling point, like pentane, is added to the mixture. When the gas boils, it expands. Which then makes the plastic molecule spread out, like you see with packing peanuts. Here are the other 3 Big 6 polymers. Polystyrene is used for CD cases, foam cups, or egg cartons. Notice that once again it looks a lot like ethylene, but instead of that 4th hydrogen, one of the atoms is replaced by what's called a phenyl group. Polypropylene is also similar to ethylene, but instead of that 4th hydrogen, it has a CH3 group, which is also called methane. These are used for bottle caps, margarine containers, and carpeting. The sixth type is polyethylene terephthalate. These are used in soft drink bottles, fleece, and carpets. Notice that this one looks different, way different than the others. As a result, the different reaction must happen for the monomers to link up. I'll discuss this in more detail later. Notice on the left-hand side, there are triangles and a number. You may have seen this on plastic containers. This is to inform recycling plants what type of molecule it is so that they know what it's made of, so they know how to recycle it. As we saw in previous slides, the hydrogen was sometimes replaced by some other atom or group of atoms. These can greatly alter the compound. These different groups are called functional groups. One way to differentiate between polymers is to look at their functional groups. These are distinctive arrangements of atoms that impart characteristic chemical properties to molecules that contain them. They are considered groups because molecules that have these atoms in similar arrangements often show similar characteristics and reactivity. Now let's return to the big six polymers. The last one was polyethylene terephthalate. It was different than the others because instead of having only one monomer with a double bond, there were two and they were single bonds. These two compounds were ethylene glycol and phthalic acid. Instead of going through addition reactions, these compounds went through condensation reactions. Notice that there's water here. You may recognize the word condensation as the water on the window in the morning. Well, this is related to the fact that it also has to do with water. The molecules come together and then water is released. Notice in this picture, these two molecules, when placed next to each other, have hydrogens on the first molecule and OH on the next. These three atoms come together to make the water. In the process, the area in which they came from gets linked together. So notice here now, it was CO, that's still there. And that's still there. Just the H and OH came together and made water. This keeps repeating to form a chain. If we go back to our list of functional groups, we can find amines and carboxylic acids. If both of these groups are on the same compound, they're called amino acids. So here's an amine and here's a carboxylic acid. They come together, it's called amino acid. Notice in amino acids, there's both a nitrogen and a COOH group. Amino acids are the primary components of proteins and nylon. There are only 20 amino acids occurring naturally, and they only differ from one another by the R group. R is a generic symbol for any organic group. Think of it as the X in algebra. These two go through condensation reactions to form polymers. Proteins are long chains of amino acids joined by condensation polymerization. Notice the word condensation. There's the water again. Notice that there's an OH group on one side and a hydrogen on the other. These three atoms come together once again to form water. In the process, a peptide bond is formed. The peptide bond is a covalent bond that forms between carboxylic acid and the amino acid of one amino acid and the amine group of the next. So if we look here, there's one compound. It's still there. Here's the other one. It's still there. So that bond between them is the peptide bond. This reaction is repeated over and over in biological cells to form proteins. Nylon is another example of a condensation polymerization. This synthetic example was created by a scientist in the DuPont company. Notice how the OH and H come together to make water. This reaction continues to form long chains with these alternating monomers. The Environmental Protection Agency, or the EPA, has been keeping statistics of the municipal solid waste or garbage for over 30 years. This includes everything you discard or throw into the trash, including food scraps, grass clippings, old appliances. This does not include industrial waste or waste from construction sites. These are included in other statistics. U.S. citizens average just under 4.5 pounds of waste per person per day. 4.5 pounds. This graph shows the average breakdown of the waste that we produce. 31% of it is paper. The food is actually 12.7%. We waste a lot of food. This is a shame, knowing how much we spend on food and how many people in this world are starving. And 12% of our waste is from the plastics. Fortunately, we recycle about 1 pound a day per person. And this number is increasing. We recycle glass, cardboard, plastics. We even reuse our grass trimmings and food scraps in compost. Unfortunately, most of our waste either goes into landfills or incinerators, which both have issues. They can produce greenhouse gases, leak, are expensive, and other issues. Even with biodegradable products, they do not completely break down in landfills. Most waste disposal areas are covered and lined to reduce leakage of the materials into the groundwater. This also discourages bacteria and fungi from doing their jobs of breaking down the waste. Luckily, we have become more conscious as a society. We have dramatically increased our recycling efforts. We are now over 30% of our waste being recycled, and this number continues to grow. Not only are we making a bigger effort to recycle, but more things that we use are able to be recycled. However, this graph does not show the whole story. If we compare the amount of pop bottles being recycled to the amount being produced, we see that we are actually recycling a smaller percentage than we were before, even though we are recycling more plastic than ever in the U.S. That just basically means we're using it more too. Only 20% of our pop bottles are making it into recycling bins, where 33% of pop bottles were being recycled before. This may also have something to do with the obsession for bottled water now. So how can we help with this issue? Most people believe that recycling is the best option. It is actually a compromise. The best option is to stop using as much to begin with. We can use less starting materials at the beginning of the product's life cycle, thus producing less waste at the end. This is also called source reduction. In this process, resources could be conserved, pollution would be reduced, and toxic materials would be minimized. That is all on page 394 of your text. You may notice that some bottles state that they use less plastic and more reusable resources in the promotion of their product. In order for recycling to be successful, it has to be efficient and continuous. The producers must create and utilize recycled materials. The consumers must demand and buy recycled materials, and then the consumers must make the commitment to recycle the used materials. As you purchase and see goods advertised, some terms may come up with items that claim to be recycled content products, which are those produced from materials that otherwise would have been in the waste stream. These include post-consumer content, which is material that previously was used individually or industrially that otherwise would have been discarded as waste. Pre-consumer content, which is waste left over in the manufacturing process, such as scraps and clippings. And recyclable products, which are simply ones that you can recycle. They do not necessarily contain recycled materials. Next time you order fast food in the drive-thru, take a look at the bag. I noticed the other day that the bottom of the bag stated some of these terms. Most of the recycled polyesters, polymers, found in plastic bottles, are made into fabrics, carpets, and shoes. There is no single best solution to resolve solid waste. But the chemists continue with their job of creating better products that use more environmentally friendly products. We have to do our job in continuing to reuse, reduce, and recycle.